Now let's look at an example from section 9.5 dealing with inferences for proportions. Here we have a pretty cool scientific advancement. Louis Pasteur had conducted a series of experiments demonstrating the roles of yeast and bacteria in the fermentation process, and it gave Joseph Lister, a British physician, an idea. Human infections might have a similar organic origin. And Louis Pasteur lived in the 1800s, 1822 to 1895. And Lister was a contemporary, living from 1827 to 1912. So he developed a theory that using carbolic acid to disinfect the surgery rooms would improve the post-operative survival rates for surgical patients. He collected some data. 40 patients were amputated with the use of carbolic acid, and 34 survived. 35 patients were amputated without carbolic acid, and only 19 survived. Now, these are raw numbers. These are not proportions. We need to make them proportions. So the first question, what proportion of patients amputated with the use of carbolic acid survived? We're going to take 34 out of 40, and we'll call that our P1, our P1 hat, which will be our first sample proportion. 34 divided by 40 will give us 0.85. If we wanted to write it in percentages, we would just move that decimal over to 85%. And then the proportion of patients amputated without the use of carbolic acid would be the 35, only 19 survived. And this will be our P2 hat, 19 divided by 35, which is 0.54, or if we were writing it as a percentage, 54%. So we're going to test the claim that carbolic acid improved survival rates using a 5% significance level. We have random samples. The sample data are independent, and then for each of the two samples, we need to check n times p and n times q. So let's write down our requirements that we need to check. We have simple random samples. We have independence. And then we need to calculate n1 times p1 hat, n1 times q1 hat, n2 times p2 hat, and n2 times q2 hat. We can do that right here. So n1 is 40, p1 is 0.85, we get 34. This is not a coincidence that 34 is my x value. My x represents the successes, so that means n2 p2 hat would be 19. To find q1 hat and q2 hat, we'll do 1 minus, so we do 1 minus 0.8 for the first sample. Multiply that by 40, and we get 6. For the second population without carbolic acid, 1 minus 0.54 times 35 gives us 16.1, 16. The big key about all 4 of these numbers is that they are greater than or equal to 5, and they are. Our requirements check out. Next, we need to form our hypotheses, and for our hypotheses in a proportion, our null hypothesis will be that the proportions are equal. Our alternative depends on what we're trying to test. Here we want to test the claim that carbolic acid improved survival rates. We want to test the claim. Since we want carbolic acid to improve survival rates, we want the proportion for carbolic acid to be higher. And over here, P1 is our carbolic acid, and P2 is our without. We want P1 to be greater, and that'll be our claim. Since we have a greater than, we're looking at a right-tailed test. We need to find our critical value and our test statistic. Alpha was 0.05. Finding our critical value is coming from our normal distribution this time, because we're doing a proportion. So our critical value, norm.s.inv, we have a right-tailed test, so we're going to do 1 minus 0.05. If you just put 0.05 in there, you'll get a negative answer, Remember, you just switch it to positive and you'll have your critical value. So we have 1.644854, which is really 1.645. And then for our test value, we'll write down the formula. Before I do that, marking off my rejection region, our test value coming from Z, P1 hat minus P2 hat minus mu1 minus mu2 all over square root P bar Q bar 1 over N1 plus 1 over N2. And we'll have to do some intermediate calculations for this. Unfortunately, there's no simple way to do this in Excel right now. P bar is calculated by adding the X's and the N's together. So I had 34 with carbolic acid surviving, 19 without surviving, total use of carbolic acid, total use without carbolic acid. And we end up with 53 over 75, which is 0.71. To find Q bar, I just do 1 minus P bar, 1 minus 0.71 will give me 0.29. I can use those values into the formula. And let's calculate this test statistic. So P1 hat minus P2 hat minus mu1 minus mu2. Remember, we always assume the null hypothesis is true. Divided by the square root, 0.71, 0.29, 1 over 40 plus 1 over 35. And I'll pull up my calculator for this. 0.85 minus 0.54 is 0.31. Calculating the denominator, 0.71 times 0.29 times 1 over 40 plus 1 over 35. And we hit equals, and we get 0.0110. Take a square root, and we get 0.1050. Now, 0.31 divided by 0.1050 will give me 2.952. And we can just keep it at 2.95 is fine. Comparing that value up here on my graph, 2.95 is very much to the right of 1.645 in our rejection region. So we will reject that null, and there is enough evidence to support the claim that carbolic acid improves survival rates. And Dr. Lister set off a revolution in medicine with his study.